Okay, so thank you very much for being here, and I apologize on behalf of Thomas. He had to attend extremely urgent family issues, so he sent me in his stead. So please bear with me. He is featuring in the presentation somewhere in a scientific meeting with me. At the end, you will see. So this is predominantly the work of Thomas in collaboration with myself and Klaus. We have been working over the last year to extend our models and put them in a highly scalable simulation tool because, as Steve just pointed out, these systems, these beasts are heavy and slow, and we need new techniques to solve them. So we are working on Moose framework, which is a framework from the Idaho National Labs. It's open source and completely scalable to CPU structures. We are more than welcome to help us in our quest for rock mechanics with dissipative feedbacks. So, as Steve briefly pointed out, geomaterials have internal structure. They are experiencing several internal dissipative feedbacks, and these feedbacks determine their macroscopic response. For example, an example inspired from geology, we all know nowadays that carbonates and calcite mylonites undergo chemical reactions like dehydration and precipitation at the nanoscale, where the microscopic chemical properties influence the macroscopic response of the material. So there is a bridge of scaling there where we have to accommodate. The same is under high velocity searing, where you can have chemical reactions altering the grain sizes and the grain properties, and influencing the macroscopic friction coefficient or the searing resistance of a fault. Lastly, but not least, this is an experiment by Jean Schulem and his group. You can see macroscopically the manifestation of chemical reactions at the clay, the nanostructure of clays between the platelets, where clays at some critical temperature dehydrate, and macroscopically they undergo thermal collapse. So this is a triaxial experiment where the stresses were held constant, and you just increase the temperature. At the critical temperature, the material collapses, expelling pore fluid water. So this is a sketch that was earlier very well described. So far, all of us have been doing sequential coupling because we didn't have the tools to do fully coupled, tight coupled systems. So we had the mechanical deformation, fluid flow through rock, which was usually impermeable, and we're trying to open the permeability. Porosity variations, chemical reactions, and temperatures all working together. We were sequentially decoupling them and trying to hope for the best, plan for the worst, and move on. Now, with REDBACK, what we're trying to do is exactly what we all want to do, make the tight coupling and have everything working together with everything else. You will see at the end of the talk that this opens us up to new types of instabilities that are only applicable in tight coupling. You cannot find them in sequential coupling, and they're actually very interesting both for the mechanical community and the geological community. So, as a dummy example, we will start with a modified CAM clay type of material. So, for anyone who is a geomechanical background, imagine a modified CAM clay. For anyone who's of geological background, let's say it's ductile carbonates. And this material undergoes a chemical reaction, so either dehydration or carbonate dissolution precipitation. And we can perform a triaxial experiment where the temperature and the confining pressure remains constant, and we are in the highly overconsolidated green stress path here. REDBACK right now has overstress plasticity implemented, but Moose has consistency plasticity in, so you are more than welcome to use your own tools and be an a la carte code. So what happens is, when you look at the specimen from the outside, the only thing that you will see is the final plastic collapse because of the chemical reaction. But because of the multiple feedbacks and the tight coupling, we can actually go inside the specimen and see exactly what happens. So in this dummy example, what we're doing is we are loading in this stress path. So at the boundary, we're loading following this stress path. And what we're monitoring here is the response of the center of the material. So what we see is that although the material starts failing in a shear direction, as we all know, at some point the interior, when the chemical reaction kicks in, the interior unloads and goes toward volumetric failure. And this is very well in accordance of what our community is recently interested in, and this is the periodic compactions. So you can see that the moment you unload, you go towards volumetric compaction. This is relatively new for us. These are insights that we never had the option of having because of the sequential coupling. Come on, move on, move on. Okay, so we have access to every state variable that we're using, like the porosity, the temperature, pore fluid pressure, and we can control. I mean, for example, you can see here, this is the mean the volumetric stress. You can see clearly that at some point you change from shear to volumetric compression. Come on. Okay, so the interesting bit is that so far there is nothing new. We know that, we know what we already knew from sequential coupling, that the mechanical, as Steve said, the mechanical deformation drives everything and the rest follows, and you can have porosity increase where you have a plastic deformation. But what happens when you couple tightly things is that you are open to new type of instabilities, like instabilities where the chemical reactions cap uncontrolled temperature increase and take over in a oscillatory instability. So you can control the well-known thermal runaway effect of shear heating by introducing a chemical reaction, and you can have periodic events where the chemical reaction releases the energy received by shear heating. Okay, so this will give you periodic instabilities in time, and it can also give you periodic instabilities in space, where every given time integral, which is controlled by the hydraulic properties of the material, you have events of high strain rate, where at the same time the porosity, so the permeability increases, the temperature decreases, and you are in a very closed limit cycle. Now, this is very important for petroleum engineering, for example, because this is the classical problem of fault reactivation, where when you pump, at some point you trigger a minor earthquake, the permeability increases and they lose the reservoir. But also, it's very important for the geodynamics community because it describes apparently a very recent finding, which is the episodic tremor and slip sequences in subduction zones. So you can see that these type of oscillatory instabilities are real, they exist in nature, and they actually carry some information for us. And these tools can allow us to actually understand better the response of Earth. I will not go into details. There is a poster session that we're running on Thursday. You're most than welcome to join, where we can discuss all these responses in detail. Because we are in a computational session, I would like to say that these are this is an open source code. You're most than welcome to help. We are outnumbered right now, so please come to Sydney or use REDBACK from your own place. It's on GitHub. We are trying to compile together a manual. You're most than welcome to help. And on behalf of Thomas, who is this guy here, with me in a first workshop of REDBACK, I would like to thank you very much and welcome you to Sydney anytime. Thank you.
Thanks, Manolis. Are there any questions from the audience?
The acronym.
Yeah.
Impressive when you.
So this is one of the stories where you first find the acronym, and then you're scratching your head to give a meaningful story. So what happens is that Moose is a framework where the developers are very supportive, let's put it mildly, that you have an animal name to your code. They're very persuasive. They can be very persuasive. So we were trying to find something, an animal that is representative of Australia, and especially Western Australia, where we were back then, and REDBACK is the obvious choice. And then it took us, and then I think it took us 6 months to find an acronym that barely fits. So if you have any better suggestion for the acronym, please. It's open source as well. Yep. As of so. That's not going to be good. Exactly. There. So we were up and then down for legal purposes, and then now we are up again as of last week. We don't have a manual yet up, so if you need anything, please contact us. The emails are there. We will be more than happy to help, and we should compile a manual, we know. But you know how it is, right? It's going to take a year.
Okay. Is there any other question? One last question from the audience? Right. If it's not the case, then...
Well, thank you very much. Thank you very much.